I was a bit late in the car. So, you have a seasonal series, you deseasonalize the series, you generate a deseasonalized series, and you put back seasonality to obtain a replica of the seasonal series. So the concept is, let me make a sketch. The concept is you have a box which refers to the observed data, and you start from a seasonal series. I display here the autocorrelation function. Then you apply deseasonalization. I use the acronym DS. And then you obtain from the observed series, you obtain a deseasonalized series. So, you start from, again, from the observed series with the periodic autocorrelation function, you apply deseasonalization and you obtain a deseasonalized observed series. Then you have the model here, the stochastic process. And you pass to the box of the synthetic data and then if we continue to look at the autocorrelation, we have the autocorrelation function of a deseasonalized synthetic series. Then you apply the anti-DS and you go back the synthetic series. It's very simple. This is the sketch. Okay, so let's now go into the details. How to perform this deseasonalization is very simple. So how to perform deseasonalization? First of all, let's remember what I said at the beginning of the lecture. Seasonality means that some statistics are seasonal, are changing along the year. And therefore, let's say a very easy way to perform deseasonalization is to make the statistics constant along the year. And I already told you that there is an easy way to change the mean of a time series. You just have to compute the mean and subtract the mean to the related observations. So in principle it's easy to change the average if we concentrate on the mean. It's change it. The problem is that in this case we don't have just a change. We have to impose a change that is varying along the year. So this is the only problem. But from a conceptual point of view, from a practical point of view, we can easily understand how to do it. So basically, we have to make an adjustment to the mean value of the data, which is varying along the year. So let's focus on this variability. Let's try to understand how the mean changes along the year. So let's suppose that we have a time series of daily data, for instance, river flows, and then we can, for instance, in an Excel file, we can represent this data. And let's say that instead of representing the data as we usually do in just one column, from the beginning to the bottom of the series, let's suppose that we represent the series by putting each year in one column. So, first of all, let's say that we have here the column of the year 2000, and then you have all the data, the daily data collected in 2000, from an index 1 to 365. Okay, you may say that 2000 was a leap year. Leap means this is stile in Italian, and therefore it's not 365 but it's 366. Usually what I do is to remove all the observations collected on the 29th of February of each year, of each leap year, because you know it's a trouble. If you don't remove this observation, it's a bit of a trouble when you try to treat a time series. So usually I remove it, because from a practical point of view, it's not really important. And then you have the column of 2001, again, and then you have as many columns that has the number of years of your time series. So you may end up, for instance, at 2012. Now it's very easy to compute here the mean value. And what do you get in this box here? You get the mean value of all the data that were observed the 1st of January. Then you can copy this. And therefore you obtain a series of mean values. And if you plot it, you may call it S, where S is an index that varies between 1 and 365. So let's put S here. And what you get is something that in our climate looks like something like this. What you would expect, because you know that in our climates, if you look at the river flows, for instance of the Po River, you know that there is an average value that increases in spring, and then a minimum in summer, and then another peak in October, November, and then another minimum during the winter. So this is what you would expect, indeed. And if you look at this average value, what does it represent? It represents the change, the variation of the mean of the year. This is exactly what we want to remove. And just because, you know, we are not interested in just the mean, we may be interested also in decisionalizing other statistics. Let's take also a similar graph for the variance, or standard deviation, which is simpler. Simpler just because it's the square root of the variance, and then you get lower values. And you would see that with some more variability, you get a similar graph. With some more variability, why? Because the standard deviation is more variable than the average. When you look at environmental phenomena, and in particular hydrologic variables, the standard deviation is more variable than the average. So you get a similar graph, but with more variability. Of course, the same graph could be done for any statistic, but usually we just focus, when we talk about seasonality, we just focus on the mean and the standard deviation. Now, the next question is, how can we, before moving to the next question, let me say one more thing, which is important. What is this graph that you obtained? If you look at the mean, what is this? This is the periodic mean. So you want to obtain an indication of how the mean is varying along the year. Now, if this is the physical meaning of this curve that is displayed here, you understand that variability, this kind of variability, is not really meaningful. It's not really physically meaningful, because you wouldn't expect that the average river flow on the 30th of April is much different from the average river flow that you have on the 1st of May. In reality, if it is changing so much, it is because you don't have many years of observations. So when you compute the average of a reduced series, then you get some estimation variability. And this is then not a variability that has a physical meaning. It's a variability that is induced by a statistical effect, uncertainty. And therefore we should remove it. So some people try to smooth, this is the term, smooth this graph, which means in Italian lisciare, regolarizzare. And to smooth the graph, the easiest thing to do is to take a moving average. And let me explain, I think you already know what is a moving average, but let me explain what is a moving average in some detail. Suppose that you have a series of data, let me write here, so let me get the box here. Suppose that you have a series of observations. 1, 2, 3, 4, 5. In this case you have 365. I didn't indicate the value of observations here, just the observation. And the moving average, first of all you have to decide the width of the moving average. Let's suppose that you want to take a moving average with width 3. This means that you substitute the first value with the average of the first 3. I use mean and average as synonyms. So you substitute the first observation with the average of the first 3 observations. And you substitute the second observation with the average of observation 2, 3, 4. You see, this is a window in which you compute the average. And you move this window along the series, so obtaining a moving average. And the moving average can be a left moving average, like in this case, because you take, or I don't remember really if it is called in this case a left moving average or a right moving average, it doesn't change much, but you understand what it means. It means that you take the average of the 3 subsequent observations, including the one that you are considering, so you are working on the right of the observation that you consider. So it can be a left or right moving average, or it can be, more frequently, a center moving average. Meaning that you substitute each observation with the average of the 3 observations that you get by considering the observation and the 2 observations that are at the sites. It doesn't make a big difference if you take a right or center or left moving average. So if you take a moving average, then you obtain something like this. And of course, you understand that the smooth thing increases if you increase the width of the window. But of course, if you increase too much the width, you get something that at the end, if you take a window which is 365, is constant. So what is the ideal width? It depends on your time series. You look at the result and you stop increasing when you see that you are satisfied. And let me give you an order of magnitude. When I work on the Po River, usually I take 20 days. So 20 is the width, the moving average that I usually take on the Po River. But you know, it depends also on the number of years during the observation period, because the variability of the seasonal component depends also on the consistency of your database. Okay, now let's suppose that you have got your estimates after smoothing of the seasonal mean and seasonal standard deviation. And let me call these estimates like mi S hat B, where the hat for me means that this is an estimate, and sigma hat S. Now let me write how to perform this visualization of the variable x, and let me introduce, in order to use a notation that is consistent, a second index for the variable x besides t. The second index would be an index s, which indicates the day of the year. So t is varying between 1 and capital N, where capital N is the total amount of observations. S is varying between 1 and 365. Now let me put to this x the subscript t, which means this is realized. And this is equal to x ts without d, minus mi hat s. What I'm doing here, I'm just subtracting the mean, with the only difference that the mean is changing for variables. And now let me divide sigma hat s. This is the visualization. So you see, it's a transformation that is very simple. Indeed, very simple. And this is just an example. The literature provides many contributions on this visualization techniques, because this is something that is indeed very important in hydrology to be able to perform a good visualization. This is just the simplest one. And it works quite well with, if you use daily or monthly data, it works really well. And if you work on monthly data, very often you don't need to perform the smoothing. And if you look after this visualization at the autocorrelation function, indeed, you should notice that it's no more periodical. And if I can fix the problem with the PC, I will show you in the next hours, the next hour after the break. I will show you that indeed it's, if you work on a periodic time series after this transformation, that correlation function is no more periodic. And what is the anti-transformation then that we can perform? It's very simple. If we want to go back to x, then it's very simple by inverting this relationship here. You can write that xt es times sigma hat s is plus E hat S is equal to X T S. This is the anti-transformation, which is very simple, of course. Okay. And this is what concerns seasonality. Keep in mind that for many types of non-stationarity, you can devise a preliminary transformation that allows you to make your data stationary. And this is the usual way in statistics we deal with non-stationarity. When we suspect that there is a form of non-stationarity, then we devise a preliminary transformation of the data. And then you may ask me, what are other forms of non-stationarity that we may experience in hydrology? And another one, which is indeed relevant, is, I want to mention it to you because it's indeed relevant and easy to deal with. It's given by the presence, the possible presence of trend. What is a trend? A trend means that if you look at the variable and you draw a plot, xt against time, you see something like this. Indeed, very often you don't see something like this because many of our scenes are stationary, and if there is a trend, usually it's not so evident. In fact, people are debating a lot on the literature whether or not the climate change is inducing trends. And they are debating because if the trend was so evident, they wouldn't debate. They are debating because the trend is not so evident. But you may experience cases in which the trend is indeed evident, and this happens frequently when you deal with land use changes. If a catchment experiences a land use change, then the trend may be very evident. And the land use change may be deforestation, may be forest fires, may be change of agricultural practices. And then indeed the land use change is much effective on the river flows than climate change. Of course, depending on the location, on the geographical location. But there are definitely more and more cases of non-stationarity induced by land use change than cases in which the non-stationarity is induced by climate change. Where climate change becomes more evident, it's when the river flow is dominated by snowmelt or glacier melting, snowmelt or glacier melting, fusione nivale or fusione glaciale. Then it becomes more evident because you know that the only, let's say, that the most relevant evidence of climate change is the increasing temperature. There is no doubt that the temperature is increasing. Some people may say that it is human-induced, some others may say that it is solar activity or other things. So some people may say it is natural, or some people may say that it's human-induced, but no doubt that the temperature is increasing. The effects of rainfall are not as evident, and therefore the increase in temperature implies for sure a reduction of the extension of the glacier and also an anticipated snowmelt. So indeed, when the river flow is dominated by snowmelt or glacier melting, then you have an evidence of changes, of trend. But when the river flow is dominated by rainfall, you know, it's really, rainfall is really not so easy to decipher. But let's suppose that whatever is the origin of this trend, let's suppose that you experience a situation like this. And so what could you do? In this case, you could estimate a linear trend, a linear regression of the data. And what we could do is to remove from each observation the result of the linear regression. Then you would get something like this. Which would be called, this one, Parte trend series. The trend series. And I'm not giving the translation in mathematical terms in this case, because I think it's to understand what is the meaning. It's just a linear regression, and we subtract from any observation the result of the linear regression. Here, in this case, there is a relevant question to pose. What is the shape of the anti-transformation? And of course, this is a bit a tricky question, because in the case of seasonality, the anti-transformation is very clear, and the seasonality repeats itself in the same way every year. So it doesn't change whether you are generating data that refer to the past or to the future. Seasonality, we assume it's unchanged. So whether I'm simulating data for designing a car, and therefore I'm referring to 2000 to 1900. So I'm referring a long time into the future. Or whether I'm generating data to verify how was the behavior of the same gun 50 years ago. So whether I'm simulating or referring to the past or the future, it doesn't change. The seasonality is the same. But if I have to guess what is the projection of this trend in the future, a trend that was estimated in the past 50 years, if I have to guess what is the projection in the future, then this becomes a tricky question, because you may assume that the linear trend will continue in the future, but you are not sure that this assumption is reliable, because the trend could also be changing. This is a bit tricky, and then you have to ask yourself what is the purpose of your simulation and what is the safest option. It's safer to continue with the trend, or it's safer to assume that the trend will stop, at least. You have to think at your practical application. You have to think what are the consequences in terms of design of each assumption, and what are the consequences in terms of risk, and then you make a choice. And this is my personal opinion, you shouldn't trust climatic models and projection that climatic models gives for the future, for the next 100 years. Because when we talk about practical design, one thing is philosophy, one thing is practical design of a dam. So you shouldn't, when you make a practical design, you should use certain information, or let's say you should reduce the uncertainty as much as possible. So it's very important that you make consideration that allows you to reduce uncertainty and risk, and not just modeling consideration. There is a very important difference. One thing is modeling, one thing is design. Modeling is certainly useful for design, but there is a big difference in modeling and design. And there may be other instances of non-stationarity. One other issue that happens quite frequently is what is called the jump in the mean. The jump in the mean happens quite frequently. It can be induced, a decrease in the mean value can be induced by water withdrawal, systematic water withdrawal from a river. Or it can be induced, an increase of the mean can be induced, for instance, by a fire. If you have a forest fire, then evaporation is reduced and you get an increase in the mean. Or there might be diversions in the river. So if one river gets captured, at least in part, you get a jump in the mean. And in this case, you know, you have to devise a suitable transformation. And of course, in this case, if the two means are constant, it's easy to devise the transformation that brings you to a stationary condition. Okay, I don't want to continue because I think I gave you enough details on seasonality. And let me now speak about, look at the slides because I want to keep yes. Let me now talk about the problem of Gaussianity. Because you may remember that we introduced some assumptions. One was stationarity, and another one was Gaussianity. We assumed that X is Gaussian. So what happens if the series is non-Gaussian? And for sure it is. When we work with hydrologic data, for sure they are non-Gaussian. Or not for sure, because if you work with annual data, they get closer to Gaussian. But in many cases, you work with non-Gaussian data. And so what should we do? Even in this case, we apply a preliminary transformation. And what kind of transformation may we apply? Of course, if you transform the data, the probability distribution changes. We know that. And we know that there is only one transformation which doesn't change only one distribution. And the only one transformation is the linear transformation, and the only one distribution is the Gaussian distribution. And please note, if you remove seasonality, the transformation is non-linear, because it would be linear if you remove the constant mean. But if you remove a mean that is changing, this is a non-linear transformation. So, we know that the transformation changes the probability distribution. So, of course, we may wonder whether it exists. Given a generic probability distribution, whether it exists a transformation that brings the probability distribution to Gaussian. And in general, the reply is yes. A transformation changes the probability distribution. So it may happen that if you have a non-Gaussian distribution, it may happen that you can identify a transformation that brings the data to Gaussian. And let me give you an example. Let's suppose that you have Gaussian data. I can generate on the PC Gaussian data, xt. So let's suppose that xt is normal. Normal is synonym of Gaussian, and this is a symbol that is frequently used in the literature to indicate a probability distribution. So this writing means xt is Gaussian with mean 0 and standard deviation 1. And let's suppose that we take the exponential of x. And what do we obtain with this? We obtain another distribution which is no more Gaussian because the exponential is non-linear. So if I apply here a linear transformation, the distribution will be still Gaussian. But given that the exponential is of course non-linear, which means that the distribution that I obtain is not Gaussian. And in fact, it's a distribution which is called the exponential distribution. And so I can write that the distribution is exponential with assigned parameters. Which, of course, depends on the original distribution and so forth. In this case, it can be It could be analytically computed, the parameters could be analytically computed, but let's forget this. And be careful, if you then take the logarithm of the exponential of x, then of course you get again a normal 0, 1. So this is a first example of a successful transformation to bring a non-Gaussian distribution, exponential x, to the normal distribution. So let's say that if our hydrological data were exponentially distributed, it would be very easy to find the transformation that brings the data to Gaussian. And this would be the logarithm. And let's say that this example, I didn't give you this example just for fun, because I made this example because this is very relevant. There are many daily river flow data, many hydrologic series, such that if you take the logarithm, you get very close to Gaussian. And this is, you may ask me why? Why this? So what is the physical reason why? If I take the logarithm of an hydrologic series, I get close to Gaussian. What is the physical reason? And I think it's nice to try to understand this physical reason because it's an opportunity for you to prove, to assess that behind statistics very often there is a physical meaning, which is very important. When you apply statistics, you have always to keep in mind the physical meaning. When you apply whatever model, behind the equations